Compound Characterization, Proton Nuclear Magnetic Resonance Spectroscopy Spectra Interpretation, Part 1. In this webcast, we will discuss how to interpret Proton NMR spectra. What information can we gain from it, and what can we use that information for? The previous webcast ended with this slide. Most organic compounds contain many hydrogen atoms, as you can see from the structure of aspirin here on this slide. We have hydrogen atoms on the aromatic ring, we have hydrogen atoms on the methyl group over here, and we have a hydrogen atom here as part of the carboxylic acid. As you might imagine just from looking at the molecule, there are many different types of hydrogen atoms. How might that affect an NMR experiment? The chemical structure you see here is of 1-propanol. The NMR spectrum you see below it is the Proton NMR spectrum for 1-propanol. By the end of this webcast, you will be able to see how this spectrum corresponds to the chemical structure. What a Proton NMR spectrum allows us to learn about a molecule are the number of unique sets of hydrogens in the molecule. We will learn this via the number of signals in the Proton NMR spectrum. We will learn about the number of hydrogens in each unique set, and we will learn this via the integration of each signal. Now, number 1 and number 2 both sound similar. Here's the difference. Number 1, the number of unique sets of hydrogens, tells us the number of different types of hydrogen atoms present in a molecule. Number 2 tells us the number of hydrogen atoms of each particular type. Proton NMR will tell us the number of hydrogens adjacent to each set. In other words, Proton NMR will tell us how many neighbors each set of hydrogen atoms has, and it will do so via peak splitting, also known as multiplicity. Proton NMR will also tell us about the presence of nearby functional groups via something called chemical shift, and finally, it will also tell us something about connectivity, where these hydrogen atoms are with respect to each other in the chemical structure. This information is given to us via something called J-couplings. For this webcast, we will focus on only these first 4 points. Before we begin, we should discuss labile protons. On the previous slide, you saw how Proton NMR can give us information about a molecule via things like the number of signals, the integration of those signals, the multiplicity splitting of those signals, and their chemical shifts. Each of those aspects of an NMR spectrum follows certain rules. Those rules are what allows us to interpret an NMR spectrum. Labile protons are special. Labile protons tend to not follow the rules that you will learn in this webcast. It is important to be able to identify labile protons and understand how they may or may not affect a Proton NMR spectrum. Labile protons tend to be acidic protons. Examples of acidic protons are protons in alcohols and protons in amines. These labile protons do not necessarily follow the same rules all other protons follow because of a process called exchange. If you look at the structure of 1-propanol here in the bottom left, we see a number of protons attached to carbon, and we also see 1 proton attached to this oxygen. Protons attached to carbon, by and large, stay in one place. They don't move. In contrast, this acidic proton, circled in red, this labile proton, does move. When we talk about exchange, we mean these labile protons exchange between molecules. You can imagine this proton being used to protonate or being transferred to another alcohol. This exchange process, this fact that labile protons tend to move around between molecules, has a number of consequences. Unlike most other proton signals in an NMR spectrum, labile protons often give broad peaks that do not integrate properly. They often have variable chemical shifts, and they do not always show coupling to adjacent sets of hydrogens. We haven't talked about these topics yet, but you will understand what these phrases mean as we go through integration and chemical shifts and coupling. Let's say we have an NMR spectrum and we suspect that we have a labile proton in our molecule. Is there a way that we can use this exchange process to figure out what signals belong to labile protons? The answer is yes. What we can do is we can add D2O to our NMR sample. Why would this help us? Remember that D stands for deuterium. Deuterium is simply a hydrogen atom that contains 1 neutron. Therefore, deuterium will exchange with the labile protons in a molecule. Remember from the previous webcast that deuterium does not appear in a Proton NMR spectrum. As a result, as this labile proton circled in red is exchanged for deuterium, the signal in our NMR spectrum that belongs to this proton gets smaller and smaller and smaller until it disappears once it has been completely replaced with deuterium. the addition of deuterium is not the only reason a labile proton might disappear. Chloroform, which is the most common NMR solvent, is slightly acidic. The practical consequence of this is that labile protons may not appear in an NMR spectrum, even without the use of D2O. Here is a demonstration of a D2O experiment. Up top, I have the NMR spectrum for this amine. In the bottom, I have the same spectrum for the same amine, but I've added D2O. How are these two spectra different? In the top spectra, I see this signal here, but in the bottom spectrum, I don't. Why is that? This is because this signal belongs to the protons in the amine. As these protons were swapped out for deuterium, this signal disappeared. This is how you identify labile protons in your proton NMR spectra. In this webcast, we will be using the NMR spectrum of one propanol to demonstrate various ideas. As we go through each aspect of a proton NMR spectrum, the number of signals in that spectrum, the integration of those signals, the peak splitting of those signals, and the chemical shift of those signals, we will use one propanol as our example. Now we will begin discussing application of NMR spectroscopy by first discussing equivalent hydrogens. When we talk about equivalent hydrogens, we are talking about hydrogens in the same chemical environment. One way to describe chemical environment is by connectivity, in other words, what atoms are connected to these hydrogens, and symmetry. Equivalent hydrogens give rise to one signal in an NMR spectrum. For example, if I have 4 hydrogens that are chemically equivalent, I would see only one signal for those 4 hydrogens. For some examples, let us begin by examining this structure here on the left. In this structure, I have drawn in all of the hydrogens. I have also already told you how many sets are present in this one molecule. It turns out that all of these hydrogen atoms are chemically equivalent. Let's talk about why that is. Let us look at these 3 hydrogens on the left first. We see that these 3 hydrogens are all attached to the same carbon. The reason that these 3 hydrogens are chemically equivalent to each other is because if I take this carbon atom and I rotate it, I can rotate this hydrogen atom to be into this spot, and this hydrogen atom into this spot, and this hydrogen atom into this spot. Because I can freely rotate these hydrogen atoms to switch positions, they are chemically equivalent. This leads us to our first general rule for determining whether protons are chemically equivalent. Hydrogens on the same carbon that can rotate, and can rotate is an important caveat, which we will discuss shortly, are equivalent. So, these 3 protons on the left are chemically equivalent to each other. These 3 protons on the right are chemically equivalent to each other. Now let us discuss why the protons on different carbons are also equivalent to each other. This has to do with symmetry. Draw a line straight down through the middle of this molecule. You will see that the left side is a mirror image of the right side. Because this molecule is symmetric, I can swap the positions of these protons simply by flipping the molecule. Therefore, these protons are chemically equivalent to these protons due to symmetry, which leads us to our second general rule. If a molecule is symmetrical, or if a part of a molecule is symmetrical, mirror image sets of protons will be equivalent. Let's show some more examples. In this new molecule, I have 2 sets of protons. Let's talk about why that is. I have these protons on the left, which are attached to the same carbon, so these are identical to each other. I have these protons on the right, which are attached to the same carbon, therefore these are identical to each other as well. Why are these protons on the right chemically equivalent to these protons on the left? This has to do with symmetry. I can flip or rotate this molecule and get the same structure back. Therefore, these green protons are chemically equivalent to each other. In contrast, these red protons in the middle, while they are chemically equivalent to each other because they are attached to the same carbon, these red protons are not chemically equivalent to the green protons. Let's go on to another example. In this structure, I have 3 sets of protons: the blue, the green, and the red. Hopefully you can see why the green protons are different than the other 2 colors. These red protons on the right are part of a methyl group. These blue protons on the left also belong to a methyl group, yet they are different colors. Why is this methyl group different from this methyl group? The reason for this is there is no symmetry in this molecule. This methyl group is attached to the carbonyl. This methyl group is attached to this methylene. Therefore, the red protons are not the same as the blue protons. Use the same logic in rings. Look at this molecule in the bottom left. I have 4 sets of equivalent protons: purple, blue, green, and red. By this point, you should recognize that the red protons are different from all other protons, and that the purple proton is different from all other protons. Now let's look at the blue and green protons. These green protons are on opposite sides of the molecule, same with the blue protons. Why are the green protons chemically equivalent to each other? This is because of symmetry. If I draw a line right through the middle of this molecule, I see that I can rotate this molecule and flip it so that the green protons swap and the blue protons swap. One final, more tricky example. Here I have an alkene. This alkene has 4 sets of equivalent protons. I have these red protons that are part of a methyl group, and I have these purple, green, and blue protons attached to the alkene. Previously, I stated that if hydrogens are on the same carbon, they are equivalent. Yet this green and blue proton have been labeled as being different. Why is that? This has to do with a caveat I said for that rule, where if they are on the same carbon and the carbon can rotate to swap the proton positions, then they are equivalent. This carbon-carbon double bond cannot rotate. Therefore, this green proton cannot switch positions with this blue proton. Therefore, they are not chemically equivalent. Okay, let's give you some practice now. Here is one propanol. Pause the video, take a few minutes, and tell me how many sets of chemically equivalent protons are there in one propanol. Welcome back. Let's see how you did. I see the protons here as part of the methyl group as being chemically equivalent. I see the protons on this methylene to be chemically equivalent. I see the protons on the next door methylene to be chemically equivalent. And finally, I see this proton as part of the alcohol as its own set. We finished our discussion on identifying equivalent sets of protons. Now we're going to talk about integration of the signals that result from those individual sets. Recall that each signal in a proton NMR spectrum results from one set of equivalent protons. What integration, or in other words, the area underneath each of these signals, tells us is the number of chemically equivalent protons that belong to that set. For example, let us look on the left side of this NMR spectrum here. I have this signal, which corresponds to one set of equivalent protons. This number underneath that signal is the integration. What this tells me is that there are 2 protons that belong to this particular set. If I go next door, I see an integration of 0.98. That's a fraction. Is that a problem? No. These values you see below are calculated by the computer and are calculated using the data provided by the experiment. Lower quality data will give us less accurate integrations. When you see non-integer integrations like you see here, you usually simply round to the nearest whole number. So in this case, 0.98 rounds to 1. So this signal here contains only 1 proton in that particular set. To go to the next signal, this signal we would round to 2. Therefore, there are 2 protons that are part of this set. And in this final signal, with an integration value of 3, indicates that there are 3 protons in this set. Now there is one caveat here. All of these integration values are relative. Remember, a computer calculates these integration values. What the computer does not know is exactly how many protons are present in each signal. All it can give us is the ratio between all these signals. For example, these signals could instead be 4, 2, 4, 6, or 6, 3, 6, 9. The computer would not be able to distinguish that. For this course, you can assume that the integration signals you see are accurate as is, unless the question states otherwise. Now let us discuss how the NMR spectrum for one propanol matches with what we have learned about what we should see. When we were discussing sets of equivalent protons, we figured out that we should see 4 signals for one propanol because we had 4 sets of equivalent protons. We had this set here, this set here, this set here, and finally this set here. Do we see 4 signals in our NMR spectrum? Yes, we do. 1, 2, 3, 4. Each of these signals corresponds to one set in our molecule. Can we begin assigning which signals belong to which set using integration? Well, let's think about it. Let us look at the signal farthest right. This has an integration of 3. Do any of our sets of protons contain 3 protons? The answer is yes. The purple protons contain 3 protons. Therefore, this signal corresponds to this set of protons here. What about this signal here that integrates for 1? What set does that belong to? That has to belong to the orange set, because the orange set is the only set that contains only 1 proton. Okay, that's not so bad. We've begun seeing how the NMR spectrum lines up with the molecule structure. What about these last 2 signals? Unfortunately, we can't identify these just yet. Both of these signals have an integration of 2. The remaining sets of protons both contain 2 protons. We're going to need more information before assigning each of these signals to a particular set. A tool that can help us do that is what is called chemical shift. The x-axis of an NMR spectrum is measured in chemical shift, usually represented by the Greek letter delta, with the units being ppm. ppm stands for parts per million. Why use such a strange unit? The reason we use ppm instead of other units such as hertz is because NMR spectrometers come in various strengths. It will be very inconvenient to have to use a different unit for every different strength of spectrometer. By using ppm, we allow all NMR spectra to use the same units, regardless of the strength of the spectrometer. To calculate ppm, we take the energy of the signal we measured from the NMR experiment, which is measured using frequency, the unit for which is hertz, and then we divide it by the strength of the spectrometer, which is measured in megahertz. Look at these units. Hertz over megahertz. 1 over a million. That's where the parts per million unit comes from. Some terminology before we continue. When interpreting NMR spectra, we often have to compare signals to each other. When we do so, we don't use the terms left or right. Instead, we use the terms upfield and downfield. For example, if I'm looking at this signal here and comparing it to this signal to its right, this signal is downfield of the signal at lower ppm value. In contrast, this signal is upfield of the signal at a higher ppm value, which you can see here. Farthest upfield, we have hydrogen atoms attached to carbons which are not near our electron withdrawing groups. We will define what electron withdrawing groups are in a few slides. For now, just know the term and know that electron withdrawing groups tend to be functional groups that contain heteroatoms such as oxygen and nitrogen. If we begin to move downfield, we find hydrogen atoms that are near heteroatoms such as oxygen or nitrogen. Not all electron withdrawing groups are equivalent. Carbonyls, for example, are electron withdrawing, but they are not strongly electron withdrawing. As a result, hydrogen atoms near a carbonyl, notice how I'm saying near, not attached to. You will see in a little bit how hydrogen atoms attached to an aldehyde or attached to a carboxylic acid are very far downfield. But for normal hydrogen atoms that are near a carbonyl, those tend to be around 2 to 2.5 ppm because a carbonyl is not a strong electron withdrawing group. In contrast, hydrogen atoms near, say, an alcohol or an amine tend to be farther downfield, from 3 to 4 ppm. If we continue moving downfield, we find hydrogen atoms attached to alkenes, hydrogen atoms attached to aromatic rings, of which a phenyl ring is a common example, and finally, farthest downfield, we have hydrogen atoms that are a part of an aldehyde or a part of a carboxylic acid. You may have noticed that these number ranges do not exactly match the numbers you see in the Spectra data tables on the cover of your laboratory manual, which you can also find on the Compass 2G course website. Those values in those tables have been distilled to this simple image, which has divided the Proton NMR spectrum into whole numbers and half numbers for your convenience. You are expected to memorize these regions. An important note before we continue: these regions are not hard barriers. It is possible for an alkene proton to appear above 6.5 ppm. It depends on what exactly is around that proton. That being said, these values for regions you see here are good rules of thumb for most spectroscopy problems. Just remember that overlap between regions is possible. Now that we have discussed at what chemical shift different types of protons appear at in a proton NMR spectrum, we are going to discuss why these different types of protons appear in these specific chemical shifts. What makes a hydrogen atom not near an electron withdrawing group so different from a hydrogen atom that is near an electron withdrawing group? This has to do with a concept called shielding. A nucleus with more electron density is what we call shielded, and shielded signals appear upfield. What do we mean by shielded? We'll talk about what shielded means on the next slide. In contrast, a nucleus with less electron density is deshielded, and will therefore appear downfield. Let us look at one propanol here on the left. Let us consider this proton here in blue. Is this proton shielded or deshielded? Remember, if you are shielded, you have more electron density. How much electron density does this proton have? Notice that it is quite close to this oxygen. Oxygen is electronegative. That means oxygen will pull electron density towards it. It is what we call an electron withdrawing group. That means this proton is losing electron density. This proton is deshielded. Let's go next door to this proton. Is this shielded or deshielded? The oxygen is pulling electron density from this proton in the middle. However, because this proton is farther away, it is not losing as much electron density. As a result, it is more shielded than the first proton, but still it is slightly deshielded. This is all about comparisons here. Let's look at this final proton on the left. Is this shielded or deshielded? This proton is very far away from this electronegative oxygen. Therefore, if this proton is losing electron density, it is losing only a very small amount of it. Therefore, this proton on the left is the most shielded of all of these. Because this proton on the left is the most shielded, it will appear furthest upfield. Because this proton on the right is the most deshielded, it will appear the furthest downfield. What about this proton as part of the alcohol? It's directly attached to that oxygen. Doesn't that mean it should appear farthest downfield of all of these? This proton is attached to an oxygen. Therefore, it is a labile proton. And labile protons tend to not follow all of the rules that other protons do. This labile proton can appear in a large range on the NMR spectrum, and it is very difficult to predict where it will appear exactly. In the NMR spectrum for one propanol, you've seen how signals have appeared at particular values on the x-axis. Where do those values come from? Those values result from a comparison to a standard. Remember how we standardized NMR spectra by using ppm as our unit for chemical shift. To decide whether a signal appears at 3 ppm or 9 ppm or 1 ppm, we make another comparison. Tetramethylsilane, or TMS for short, is used as a universal NMR standard. The hydrogen atoms in TMS are very shielded. As a result, most proton signals in an NMR spectrum will appear downfield of TMS. So what we do to make NMR spectroscopy analysis easier is we make the signals in TMS equal to 0, and then compare everything to that. If you see an NMR signal at 1 ppm, that means that signal is 1 ppm downfield of TMS. What causes this shielding effect? Why does the presence of electron density affect the chemical shift of our signals? In this diagram, I have a nuclei here, as shown by this arrow, and the electron density around this nuclei is represented by this blue sphere. Remember that electrons are charged, and that these electrons are spinning. Because electrons are charged and are spinning, they generate a magnetic field. It turns out that the magnetic field generated by the spinning electrons, shown here by this green arrow, is pointed in the opposite direction of the magnetic field we apply in an NMR experiment. Because the magnetic field applied by the electrons is in the opposite direction of the applied magnetic field, it cancels out some of the applied magnetic field. It makes the applied magnetic field weaker. This means that the nuclei feels less of the magnetic field. It is shielded from the applied magnetic field. Therefore, it appears upfield in an NMR spectrum. In contrast, if I had little electron density, I would have a smaller electron magnetic field, which would cancel out less of the applied magnetic field. That means nuclei would be less shielded and so would appear downfield. This explains why hydrogen atoms near electron withdrawing groups are further downfield than hydrogen atoms not near electron withdrawing groups. However, if you recall the general chemical shift table from a while back, you know that alkenes and aromatic protons are even further downfield, yet those don't have any electron withdrawing groups. This has to do with an idea called anisotropy. We will not discuss anisotropy in this course. Simply know that anisotropy exists, and it explains why hydrogen atoms that are part of alkenes and aromatic rings appear farther downfield than hydrogen atoms near electron withdrawing groups. How can we use chemical shift to our advantage? Previously, we had assigned several of our sets of protons. We know that the purple protons belong to this signal on the right, and that the orange proton here belongs to this signal here. What we didn't know is what signals the red and blue protons belong to. Let's use chemical shift to assign them. Let's look at the blue protons. The blue protons are closer to the oxygen than the red protons are. That means the blue protons should be less shielded than the red protons. If the blue protons are less shielded, they should appear further downfield. Which of these two unassigned signals is further downfield? The one on the left. Therefore, this signal should correspond to the blue protons. In contrast, the red protons are farther away from this oxygen. That means the red protons are more shielded, therefore they should appear further upfield. Which means this signal, further upfield, belongs to the red protons. And while we already know what signal the purple protons belong to, we could use the same logic here. The purple protons are farthest away from the oxygen, therefore they are the most shielded and should appear farthest upfield. And they do. If you go back and look at the table of general ranges that I expect you to memorize, you'll see how these signals fit into those general ranges. One final topic before we finish this webcast. Spin-spin coupling. As you may have noticed, signals in spectra often appear as multiple peaks. This signal on the left has 6 peaks, 1, 2, 3, 4, 5, 6, and the signal on the right has 3 peaks. The number of peaks that belong to each signal indicates the number of neighboring or adjacent hydrogens. The number of peaks present is called the multiplicity of the signal. If you see 1 peak in a signal, that's called a singlet. If you see 2 peaks, that is called a doublet. When I ask for the multiplicity of a signal, this is what I'm asking for. How many peaks are present? What's the multiplicity of this signal? It has 1, 2, 3 peaks. Therefore, this would be called a triplet. What about the signal on the left? There are 6 peaks. Therefore, that would be called a sextet. Before continuing, one quick note on multiplet. In this course, your NMR spectra should be what organic chemists would call clean. They will be easy to interpret. I would not expect to see many complex NMR signals that you would have to call multiplets because there are no clear patterns. Where does the splitting come from? Why do signals appear as multiple peaks? This is because the magnetic field of a proton is affected by the magnetic fields of its neighbors. For example, consider this molecule where we have proton A and proton B. If we consider proton A, it has a magnetic field which points up or points down. Proton B has a magnetic field which can also point up or point down. This means that it can be aligned with A, in other words, pointing in the same direction, or it can be aligned against A, pointing in the opposite direction. Depending on which it is, proton A is either more shielded or more deshielded. Think back to what we talked about when discussing the shielding effects of electrons. The magnetic field of the spinning electrons canceled out some of the magnetic field we apply because the magnetic field of the electrons was opposite the applied magnetic field. It's the same thing here. If HB points in the same direction, it creates more shielding. If HB points in the opposite direction, it creates de-shielding. Of course, this works both ways. If HB affects, or what we call splits, HA, then HA also has to affect or split HB. What's the consequence of this? If HA is all on its own, we would expect to see a signal with one peak. However, once we consider HB, we instead get two peaks. One of these peaks results from HB increasing the shielding of HA, and one of these peaks results from HB de-shielding HA. This is why we would see a doublet here. How close does a proton have to be in order to split another proton? Typically, although there are exceptions, only vicinal protons, in other words, protons that are on adjacent carbons, will split each other. Here, HA and HB are vicinal. They are on adjacent carbons, therefore they split each other. As you might expect, labile protons tend to not follow this rule. Usually, labile protons do not cause splitting and are not split themselves, even if they are vicinal to other protons. Now that we understand where splitting comes from, how do we know how many peaks a signal should appear as? To make this prediction, you use the n+1 rule. If hydrogen A has some number of neighboring equivalent hydrogens, which we're going to designate by n, and the number of peaks in A's signal is n+1. For example, if there are no neighbors, then I will see only one peak in my signal, a singlet. If I have one neighbor, like I saw on the previous slide, I should see two peaks, a doublet, where 1 + 1 is 2. You can use this equation in reverse as well. If I have a quartet, 4 peaks, I know that the protons in that signal must have 3 neighbors. Let's see if the n+1 rule matches what we see in the spectrum for 1-propanol. Let's look at the purple protons first. How many neighbors do the purple protons have? Well, let's look at the vicinal carbon, the next door carbon. How many protons are attached to this carbon? 1, 2. The n+1 rule says there should be 2 + 1 peaks, 3 total. Does the signal corresponding to the purple protons show up as a triplet? Yes, it does. Now let's look at the red protons. How many neighbors do the red protons have? Well, we have to look to all vicinal carbons. There's a vicinal carbon to the left and a vicinal carbon to the right. So we have to count all of those protons on those carbons. We have 1, 2, 3, 4, 5. So the n+1 rule says I should see 5 + 1, 6 peaks, a sextet. Does the signal corresponding to the red protons show up as a sextet? Yes, it does. Now let's look at the blue protons. I have a vicinal carbon to the left, which has 2 protons. But what about this proton to the right? Does that split our blue protons as well? No, because this is a labile proton. Labile protons do not cause splitting. That means the blue protons have only 2 neighbors, which means I should see a triplet. Do they show up as a triplet? Yes, they do. One final note, notice how the labile proton shows up only as a singlet because it is not split by any adjacent protons. To recap what we have discussed in this webcast, proton NMR spectroscopy allows us to learn a great deal about the structure of a molecule. The numbers of signals we see tells us the number of different kinds of protons present in the molecule. The integration of each signal tells us the number of protons that contribute to that signal. The chemical shift of the signals gives us information about what kind of protons are present. And finally, splitting provides information about the number of adjacent protons.